Okay. I still have whoever has the username Zoom user. That's the only person that I didn't give attendance credit for because I'm not sure who you are. Let me see. Is he still here? I don't see him. He's probably trying to change his name. Okay. Well, everybody else I have. Let's see. So there's one person in here unaccounted for. Student. Hang tight. We'll start in just a moment. There's one person. I think he changed his name. I just got to figure out who it is. That one got him. Got that one. Let's see. Is that who it is?
It was me, Leighton Davis.
Yeah, I got you. He said that as soon as I found you. Yeah. Okay, I think we got everybody. Okay, we're looking good now. Yeah, I just wanted to make sure everybody got their attendance credit. I didn't want you to be here, and then it's like we're there today when you were here. Yeah. So anyway, we got everybody. So okay, let me see. It's that time. Let me see. So welcome back. Hopefully everyone had a good weekend. Man, I just be like in my own world. I'm like I'm still on weekend mode. This is my first class for the day, and it's like it's just weird because it's late. Let me see. No major announcements. We're just at the top of week 4. Uh, yeah, nothing major. We're just gonna kind of keep going. All right. So I think our first exam is at week 6. Once we get through chapter 2, I know this week. So we're going to be starting chapter 2 this week, right? So we've done our introduction to derivatives. Remember, our goal for the semester is to get through the first four chapters of the book. We want to get through integration. So we've kind of touched on the topics for differentiation. We introduced it as the derivative is the slope of the tangent line at a point, and we kind of built the backstory to that, right? Because if we think about a curve and a point on the curve, if we try to manually draw a tangent line, there's some wiggle room, right? So it's kind of hard to find the exact tangent line if you're doing it manually. So that's where this technique of, if you have a second point and the limit definition, the limit as h tends to 0, the difference quotient, that whole thing, as that second point gets closer and closer to the first point, then we get a better and better approximation for the slope of the tangent line. So we take the limit as h tends to 0, yada, 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 right? But so that was how we introduced it. Then we got past it. Then we started looking at differentiation techniques, all right? So like we had the power rule, chain rule, product rule, quotient rule, all that kind of stuff, right? So that was an introduction to differentiation. So then here with chapter 2, we want to take it a little further and apply differentiation techniques to exponential and logarithmic functions. Okay. As usual, if you have questions, feel free to unmute yourself to get my attention, and we can talk about it. And I'll check attendance again for anybody in the waiting room. All right. That's a little bit. I was being a little bit redundant. Anybody waiting in the waiting room, right? So anyway, I'll check for the waiting room in about 12 minutes. Just about 6:15. So if you have a brother that's in there, just tell him to just stay there. Just wait. Okay. So let's see. Okay. So with section 2.1, we'll work on exponential and log functions of natural base E. Okay. So a few objectives. 1, graph and solve exponential functions of natural base E. And then 2, graph and solve logarithmic functions of natural base E. Okay, that's fine. So the natural base E, denoted E, is the value given by the limit as n tends to infinity of 1 plus 1 over n to the power of n. And so when you evaluate that limit, you eventually it gets to this decimal approximation. That's 2.7182, yada yada yada. Let's kind of keep going. There's more I want to say there, but we don't. That's just kind of, we don't really need that. But let's just give you a little backstory on how that number is generated, where it's coming from. Okay. So then the quantity P growing continuously at an annual percent rate R expressed as a decimal has a future value after T is given by this, right? So this is like, well, I was about to say it's like a continuous compound interest, but it's more like exponential growth model, right? They're the same. It's just one applies to finances and this applies to like population growth or something that's growing exponentially. Okay. So Lewis invests $5,000 into an account that earns interest at an annual rate of 3.25%. Find the future value of Lewis's account after 5 years. The interest is compounded continuously. So when we do continuous compound interest, that's what we use. I remember that formula as PERT. It's essentially the formula that we saw on the previous slide. Okay. So this is kind of from like college algebra right now. So continuous compound interest. I usually like to do formulas in the green. Let me see. A of T, again, I remember it as PERT, P e to the RT. Okay. Let's see what components we have. So it looks like its principal is $5,000. Try to keep this open. So let's take the principal is $5,000. Okay. The rate is 3.25%. So we do need to express it as a decimal. So if we move the decimal to the left twice, 325. We're trying to find A for the future value. And the time has been, I'll put it here, 5 years. Okay, and it's compounded continuously. All right, so since we're doing continuous compound interest, we use this PERT formula. Right, so then we want to find the future amount after 5 years. We say, so the principal is 5,000 times E to the power of 0.0325 to the times 5, right? I think I'm just going to use my calculator for that. So I got like about 9 minutes. Reload and refresh. Your man has just been low. Like, I don't know. I slept like half the day. I was like, man, why can I not wake up today? What is going on? I don't know. But I mean, I feel rested. I just don't feel energized. I don't know if it's probably because it's overcast. I know that has a lot to do with the times 5. And so basically I'm just typing, 5,000 times E to the power of 0.0325 times 5. Future amount after 5 years, 3%. So probably like 6,000, 5,000. Okay. So since we're talking about money, we'll go to 2 decimal places. 5882. And we'll say 24 cents. Again, as usual, if anything is not clear, feel free to unmute yourself to get my attention and we can talk about it. Okay, let's get rid of this. 5882.24, 5882.24. Okay. So again, that was from college algebra, just an application of continuous compound interest. Okay, let's keep going. I'm going to leave this as an exercise. So for any positive number x, the natural log or log base e of x is given by this, right? So the natural log is just the common log base e. Okay. So, you can either work it in terms of natural log. Just keep in mind that that's the same as common log base e. Sometimes we'll switch it to this form. It just depends on, the context and what we're doing. So then, for instance, if we have y equals the natural log of x, and keeping in mind that that's the same as y equals log base e of x, well, I think we talked about how to convert from log form to exponential form, the base of the log swings over and becomes the base of the exponent, and that's how we get e to the power of y equals x. Okay. So find each of the following. If necessary, use a calculator to approximate the values to 3 decimal places. So in the first part, natural log and e, the exponential e, they're inverses of each other, so they cancel each other out. So that result should just be 4. Okay. Natural log of 1 in general is 0. Okay, so again here, natural log and e cancel each other. So then it should just be -1. And then the last one, we'll just use a calculator there. So we said the natural log of 20. 3 decimals, so 996. Okay, we still got about 5 minutes before I check attendance again. Okay. All right. So I feel like these weren't too terribly bad. 4, 0. We got our 4, 0, -1, and approximately 2.996. Okay, I feel like those weren't too bad. Let me see. So, so properties of the natural log. So, you know, the log of a product can be rewritten as the sum of the logs. The log of a quotient is the same as the difference of the logs. The log of a power is the same as the power times the log. The log of e, they cancel. Keep in mind, there's an implied 1 here. So since natural log and e cancel, then we're left with the 1. Properties 1, 2, and 3 require that m and n are positive. Okay. The log of 1 is 0. Then we have here is the change of base, is property 6. So if we say the log of m base b, that's the same as the natural log of m divided by the natural log of b. And let me see. I feel like there's something missing here. I think that's supposed to be log of m base b. Yeah, I think this is a typo. But basically it's a change of base, right? I'm gonna augment this. I think this is supposed to be log base b of m. Yeah, let's just go with that, right? Okay. Again, with this one, natural log and e cancel, so that comes down, and we're just left with the power there. The same thing here, e and natural log cancel, so we're left with the inside part of the log. Okay, let's see if we can see this in action. Let me see the time. We still got like 2 minutes. Given that the natural log of 2 is this and the natural log of 3 is this, use the properties of logs to find each of the following. The log of 6, right? That's the same as what? The natural log of 2 times 3. So then the log of the product is the same as the sum of the logs. So we can write this as the natural log of 2 plus the natural log of 3. So then that's going to be that 6931. What am I writing? 6931 plus 986. Let's see, so 7, 1, carry the 1, 10, 19, carry the 1, 7, 1. I think that's right. I'm gonna go with it. 81 is what? Is that 3 to the power of 4? 9 times 9? So that's the same. This is the same as the log of 3 to the power of 4. So then we can apply the power rule. So then the power can come down. So then this is going to be the same as 4 times the natural log of 3. So it's going to be 4 times the 1.0986. Let me see. I'm guessing this is it. Just me doing a little bit of mental math. As soon as I finish this example, I'll check for attendance again. So then if we apply the quotient rule, the log of the quotient is the same as the difference of the logs. So this is going to be the natural log of 1 minus the natural log of 3. The natural log of 1 is 0. Natural log of 3 was given 1.0986. 1.0986. Okay. So the log of the product becomes the sum of the logs. This is going to be the net 2. Plus, I'm going to go ahead and apply the power rule. So that's going to be 5 times the natural log of E. So it's really just the natural log of 2 is the 0.6931. The natural log and E, they're inverses, so these guys cancel, and it leaves us with just a 5. So then it looks like the final result is 5.6931. And again, you know, you don't have to like follow every little step that I'm doing. I'd rather you just kind of like just try to absorb what you can and just kind of like let it be conversational. And you really won't see it until you kind of take these and try it on your own. If you try to follow every little thing that I do, it can be a little bit like, I don't know, mind numbing. So just try to like absorb, get the gist of it, and you really don't see it until you try it yourself. We can use the change of base formula for E. So this is gonna, we can, like in a calculator, we can just do the natural log of 3 divided by the natural log of 2. Or we could have done the log of 3 divided by the log of 2. We should get the same result in either case. 5849, so 5850. Okay, let's see how do we do with these numbers. And I'll check attendance. Let me see. 1.7917. Okay. 3944. We got that one a little off. 3944, 39. Let me check it again. 6 times 4 is 4. Carry the 2. 32. Oh, that is a 34. Okay. I think that's the only thing. I'll just change it here. It's a 4. Put it in purple. 3944, that's fine. Negative 1.0986. Okay. 6931.5. Did I get that one wrong? I think I got that one wrong. Oh, we got it. And then 1.5850. Okay. 51. Let me. No, they probably did some rounding somewhere. 5849. That's definitely 5850. Oh, you know what? I know what they did. The reason it's different because they rewrote log of 3 base 2 as the log of 3 divided by the log of 2. So they use those given results. So they use the 1.0986. Sorry, 1.0986 divided by 6931.6930. Oop. 6931. They use those numbers. Yeah, 5851. Yeah. So, you know, it's okay. Yeah, that's fine. Okay, let me check on the gentleman in Zoom real quick if I can get my device to work. Okay, let me. Trying to charge it while I work, but it definitely is less responsive when it's charging. Let's check here. We got a good amount, looks like. Okay, let me try to get these gentlemen. Ooh, let's see. Okay, cool. Definitely see some familiar names here. Hope everyone is doing well. Ooh, we got a good amount. Okay. I mean, that's there now. Okay. All right. Let's let everybody in. Come on. So it looks like we got the total of 22. Go here. Right. Absent. That looks proper. Okay. Look, looks good. Let me see if I go here. I can see it. I think we're good. Okay. All right. And, if somebody just happens to be late, like that's missing, we'll play by ear. Okay. So we got these. All right. Oh, I keep forgetting that we do have another section we need to get through. Okay. Let's keep going. So the theorem 3, natural log of x exists only for positive number x. The domain is MC. All right. So the log is only defined for positive numbers, right? The domain is going to be 0 to infinity. Ln is natural log of x is less than 0 when x is between 0 and 1. Is equal to 0 when x is 1. And it's positive when x is greater than 1. The natural log function is always increasing and the range is all rails. Right? So those are just properties of the log function. Find the domain. Okay, so in general for a log function, the domain is the set of positive real numbers. So in other words, what we're saying is this inside part, this 5 minus 2x has to be strictly greater than 0. We can't take the log of 0, nor can we take the log of negative. So the inside part has to be strictly greater than 0. And then if we solve, 5 is greater than, what is that, 2x. Divide 5 over 2 is greater than x. Okay. So then if we wanted this in interval notation, I usually like to draw the graph first. Here's our 5 over 2. So if the alligator's eating the bigger thing, all right, that means our numbers are smaller than this. So that means our numbers go to the left. Okay. Let me see. And then because there's no bar, we should use either an open circle or parentheses. Okay, so now that we have the graph, I feel like this is the easiest to translate it into interval notation. So the far left is going to be negative infinity up to 5 halves. Infinity always gets a parentheses, and in this context, the 5 half gets a parentheses as well, because there's no bar. If there were a bar, then the 5 halves will get a square bracket. And so in context, what this means, parenthesis means what? We get really, 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 really close to that number, but we don't include that number. Versus a square bracket means we get really, not only do we get really, 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 really close to that number, but we do also include that number, right? So then we can actually check this. Well, yeah, we can check it. So like we can choose several values that should work. Like for instance, if x is 0, that should work. So we would take the natural log of 5, right? We get a real result. But if we choose something to the right of 5/2, what is that? That's 2.5. So if we chose a number like 3, it should not work. If we plug 3 in, 5 minus 6 is going to be what? -1, and we can't take the log of negatives. Right? So just you can choose, if you choose something in the set, you should get a real result, or you should get a real number. If you choose something outside the set, you're going to get an error. Something I just feel like, let me check real quick. I think we're good. Chat looks good. Let's keep going. Okay. All right, I think we got that result. Oh, that was another one. Oh, quick check. That's a quick check. Okay. Solve the following exponential equation using logs. Give answers to 3 decimal places. Okay. So then for part A, we have e to the power of 3x equals 2. So what we can do is take the natural log on both sides. On the left-hand side, this allows us to bring this out of the power, and these guys are going to cancel each other. So on the left, we're gonna have 3x. On the right, we have the natural log of 2. That's just some number. And then I'm gonna divide both sides by 3. So we have whatever that number is divided by 3. And then we would just use that calculator. Natural log of 2 divided by 3. Okay. 231. Just gonna give myself a little bit of space. So that was A. And then B. So we're starting with this 250, e to the 0.015 t equals 750. Okay. So we're going to use inverse operations to constantly move things. We're trying to isolate the t, right? So first we have that 250 times the exponential. So the inverse of multiplication is division. So we're going to divide both sides by 250. Okay. So then on the left, it looks like we still have this e to the power of 0.015 t. And on the right, 75 divided by 25, what is that, 3? Okay. So then if we want to get that out of the power, right, just like we did in part A, we take the inverse of e is going to be natural log. So we take the natural log on both sides. These are going to cancel. This allows us to bring this in front. So now at this point, we have 0.015 t. And on the right, we just have whatever that number is. So then ultimately, t is going to be whatever that number is divided by this. And then from there, we use a calculator. Yeah, sorry, guys, my energy is low. Like I'm trying to just like I'm like this is one of those days like my energy is just shot. Divided by 0.015. Okay. 3 decimal places, 241, so 73. Paste. Okay. 231, 73, 241. 231, 73, 241. That's fine. Yeah. Okay, let's keep going. We're almost done. I think I'm gonna just kind of power through this one. So the goal for today was get through the first 2 sections of chapter 2, right? I think chapter 2 is the last chapter where we need to do 2 a day for the most part, and then after chapter 2, the rhythm is going to change a bit. But I think it's pretty much whatever's in the syllabus. Like that's pretty much what I'm following. The exponential growth rate are expressed as a decimal, and the doubling time are related here. Okay. So the doubling time, I usually just use this guy. Let me see. So the doubling time is going to be equal to the natural log of 2 over r. All right. I just go from there. And then I can generate the others, right, through algebra. Okay. We'll come back to that. So Facebook connects people with other members they designate as friends. During this period of heaviest growth, membership in Facebook was doubling every 6 months. What was the expected growth rate of Facebook membership as a percentage? Okay. So we just said that the doubling time was what? The natural log of 2 over r? Let me see. It was doubling every 6 months, right? I think usually doubling time is usually in years. So if it's 6 months, that's what, half a year? What was the growth rate as a percentage, right? So basically we need to solve for r. So we can like cross multiply, or that's a half. So we can actually, I mean, cross multiply is probably just the fastest, easiest, right? So then r equals the natural log of 2 over a half, right? Which is really, this is really the natural log of 4, right? Because a half, when you divide by a fraction, you do keep, change, flip. So the natural log of 2 divided by half is the same as 2 times the natural log of 2. But then we can apply the power rule. So you can move that 2 to the power. So it's going to be the natural log of 2 squared, which is 4. Or in your calculator, you can just put the natural log of 2 divided by half. Either of those should work, right? And we can check it here, just to confirm that both of those are the same. We could have just done the natural log of 2 divided by half. We get this result. We could have also done natural log of 4. We should get the same thing. Okay. Let me see. That's as a decimal. So what, we move it to the left? 2 spaces? Wait a minute, am I getting it backwards? Because normally they give it to us as a percent. We move the decimal to the left twice. So I think we might actually need to move it to the right by twice, by 2 points. So then 138.63%. Guess that makes more sense because it was popular, or it is popular. 138.63. See, I think that's proper. Let's go with this. And I think this is okay. Let me see, 6. Oh, they left it in months. Okay, we converted ours to years. Okay, per month. Okay, so if this is per year, then we can take this and divide it by 12. Let me think. Is that percent per year? Yeah, so if we take that and divide it by 12, we should get their result. That'll give us per month. 1155. Yeah, 1155, right? So this was per year. This was per year. If we want it per month, we divide by 12. All right. And that's how they got their result. Theirs was per month. They left it in terms of months, which is fine. Okay. So then we're asked to solve this. Okay. So again, we're going to be using this. We're going to be using inverse operations to basically isolate the x. So I think I'd want to just get a copy. 5 plus 7 times the natural log of x plus 3 equals 19. Okay. So then what? Since we're adding 5, the inverse operation is going to be subtract 5. I'm just going to put the result. So if we subtract 5 from both sides, we get a 14 over here. Then what? Since we have 7 times the log, the inverse operation is going to be what? Division. So we divide both sides by 7. I think the AC just came on. It got cool all of a sudden. Weather's been like kind of funny. It's like either it's be really cold or it's rainy or it's it was kind of warm one day, a little bit. Kind of nice. All right, so then if we want to get rid of the log, remember log is this natural log is the same as common log base E, right? So let me do it this way. So natural log is the same as common log base E of this. And then we can rewrite this as an exponential. We take the base of the log, swing it to the other side, it becomes the base of the exponent. Or we could have just done e to the power of the log equals e squared. The e and log would cancel, right? In either case, this is our next step. E to the power of 2. Okay. So then ultimately we get x equals e squared minus 3. That's the exact result. And then we use our calculator to crunch that number. Okay. E is second ln. We want to say to the power of 2 minus 3. We'll just do 3 decimal places. 389, so 4.389. Okay. We should plug it in to check. Just in the interest of time, I'm just going to use my prepared notes. 389, 389. And so this is just a type explanation of what we just experienced, and then with like a little written justification for each step. Okay. Okay, I feel like this is okay. And yeah, we made it to the end of this section. All right, so I'll let you kind of go through this on your own. Let me go ahead and make a copy of this available because we kind of need to go into the next section. You're not going to work. Thank you. Share. I like to send it to box right here. I need the right folder. I know that's not the right folder. Oh, this is the spring of 24 traditional calculus notes, handwritten notes. So yeah, week 4. Yeah, we're on chapter 2. Okay. So when this bar finishes loading, you'll be able to access a copy of anything that you saw me writing. And let's go ahead and pull up section 2.2. Okay. Hopefully you guys are okay. You're a little bit more quiet for my liking, but you know, that's just the nature of it. I mean, I am here if you have questions. Hopefully you're subscribed to my YouTube channel with your notifications turned on. I think I did have, but I think it was another class. Just also as you kind of make your way through the homework, don't hesitate, or feel free to use the Ask My Instructor. And basically, like what that is, it takes a screenshot of whatever question you're working on and it emails it to me. And then, just whenever I see it, I make a video response. It's kind of walking you all through it. Okay. So let's continue with section chapter 2 with section 2.2, derivatives of exponential base E functions, right? So 2.1 was it should have been like a review from college algebra 2, or yeah, I think college algebra 2 on exponentials, right? So now we want to start to explore the derivative of the exponential, right? So a few objectives here. 1, differentiate exponential base E functions. And 2, solve applied problems involving exponential base E functions and their derivatives, okay? The derivative of the function E is itself. So in other words, f prime of x equals x, or d by dx of e to the x is e to the x, all right? Yeah, so that's, because of that property, E is its own derivative. which means that if we had the function e and we found the slope of the tangent line at any point, it's going to be whatever the x value is, right? Whatever the x value is on that graph, when you find the slope of the tangent line at that value of x, it'll spit back out the value of x. So because e has that unique property, we tend to, it's a major thing that we study. We tend to focus on it for a bit, right? So here we're asked to find the derivative of y with respect to t. Maybe they meant x because none of these have t. I think they're supposed to be find dy by dx. Let me kind of look here. Yeah. I think they meant d by dx. Yeah, it's supposed to be d by dx. Okay. Here, it's supposed to be dy by dx. So the derivative of y with respect to x, okay? And for part A, dy by dx. So the derivative of e is itself. So then it's just going to be 3e to the x. Let's see. I don't think we're doing that just yet. Yeah, okay, we're okay. Paste, nice. Okay. So then for B, okay. So we have that our y, we have x squared times e to the x. So when we go to take the derivative, we got to apply it to see if you can remember how that goes. Hopefully, you start to learn these rules. It becomes like you start to know them like the back of your hand just through repetition, right? So first it's like kind of figuring it out a little bit. And then the more you practice, the more it becomes second nature, right? If it's not second nature, then you just haven't practiced enough. And that's like with anything. All right. So here, the product rule goes what? The first times the derivative of the second plus the second times the derivative of the first. Okay. So then when we go to find dy by dx, the first, which is this guy, I feel like I need more space. Let me, we're going to move this here. So the first is this guy times the derivative of e. So the first times the derivative of the second. E is its own derivative. Plus the second times the derivative of the first. Right? And that's the product. We could factor out the e to the x. And we're going to be left with x squared plus 2x. So it might have it in either form, either that first line or the second line. They're the same. Right. Okay, that's fine. I'll keep working here for C. Okay, so I think B was the product rule. So then C looks like it's the quotient rule. So just take a moment to yourself to see if you can recall the quotient rule. And that's the one to me sounds like a yodeler, right? So the quotient rule is low D high minus high D low over low low. That's what I always think of, like a yodeler. And then that sound just makes me think of, I guess it was Trolls 2, Band Together. No, not Band Together. World Tour, where the yodelers, like, I love that music. Like, it was like when they did the yodeling in that. I don't know. It's just, I like the way it sounded. It just had this funky modern and traditional mix. It was different, weird, but I liked it. It was interesting. So anyway, so again, with this one, the quotient rule is low D high minus high D low over low low. So when we go to find dy by dx, low is this guy. The derivative of the top is itself. So low D high minus high D low. The derivative of the bottom is 3x squared all over the bottom squared. So there's going to be, we'll leave it as x cubed squared, right? For now. Let me see. It looks like on the top we can factor out. They both terms have e to the x and an x squared. Because we might be able to get something to cancel. Okay. So it looks like we can factor out an e to the x times x squared. We're going to be left with, it looks like there's an x in the first term and a -3 in the second term. Now, if that's x to the power of what? We multiply, yeah, x to the power of 6. We can rewrite x to the 6 as what? X to the 4 times x to the 2, right? So x to the 6 is going to be the same as x squared times x to the 4, right? And I did that because that will allow us to cancel these guys. Okay. So then the ultimate, or the final, we get, on top we have this e to the x times x minus 3. On bottom, it looks like we have x to the 4. Okay. Paste. So, it can get a little bit dicey with these, give yourself space, plenty of blank space, write kind of big. Don't write like super small, because it's a lot harder to follow. It's easy to lose track and to make a mistake when you're kind of like writing small and kind of sloppy. Just slow down, take your time, and just take it, part by part, bit by bit, right? But it does require you to like take your time. Like you have to slow down. Just taking charge of the rhythm when you're working on this, it makes a big difference in processing the stuff. And this topic, this kind of material or content is not for your average bear, right? Because most people, again, this is like beyond a microwave generation where, the microwave generation, we sit in front of the microwave like, yo, what's taking so long? This is taking too long, right? In a rush, in a hurry, can't slow down, that kind of thing. This requires you to like slow down, Okay, so I feel good about this. E to the x squared plus 2x. E to the x squared, okay. And then e to the x minus 3 over x to the 4. Yeah, all right. Okay, I feel like there should be questions, but again, if you do have questions, feel free to unmute yourself to get my attention. Let me check on you guys in Zoom. You can also type in the chat. I do monitor the chat. I think you guys are good. The chat looks good. I think everybody's here. Yeah, you guys look good there. Okay, let's keep going. Okay, now we're actually making good time with this section. Quick check I leave as an exercise for you. So we saw in these past couple of examples where, E has the exponential function E has a unique property where it is its own derivative. So in other words, f prime equals f. So then now we want to explore what this is like an extension of that derivative, where instead of having e to the x, we have e to the power of some other function. So then it's the same derivative like we did just a moment ago, but then you have to extend it like the chain rule. So it's like it's similar to the chain rule, right? So when we take the derivative of e to a function, it's still going to be itself, but then times the derivative of whatever that function is. It's basically like an extension of the chain rule. Okay, and this is the same thing, just articulated a different way. The derivative of e to some power is the product of e to that power and the derivative of that power. Right? Something. What is the source? Is it the trash? It's probably the trash. I definitely got some stuff in there that needs to go outside. Those dishes.
You and Jack used to be.
Okay, thank you. Okay. All right, let's keep going. I differentiate each of the following with respect to x. Okay. So then for A, so dy by dx, E is its own derivative. Then we got to say times the derivative of the power. So just basically times 8. Because the derivative of 8x is 8. Okay. So that would be, well, I should have space. Let me work here. Okay. So if we say dy by dx, e is its own derivative times the derivative of the power. I am going to move this. I'm not liking how this space is working out. The derivative of that power, negative 2x plus 4. That's it. We just leave it like that. So again, for these, we're just saying the derivative of e is itself times the derivative of the power. Okay. We can work c here. So then our dy by dx, e is its own derivative, e to the power of x squared minus 3. And then we're going to say times. So the derivative of that function, it looks like we got to apply the chain rule again, right? So the 1/2 comes down. We still got this x squared minus 3. That's now to the power of a negative 1/2. And then we need to say times the derivative inside of that, which is going to be what? 2x. Okay. So then if we kind of rearrange this, on top, it looks like we have, let me do the bottom actually. So we have this 2 times the square root of x squared minus 3 on bottom. Those two are on bottom. And on top, it looks like we have this 2x times e to the power of square root of x squared minus 3. Okay. So it looks like these 2's cancel. I'm just going to erase them just because I'm running out of space. I'll strike through them because I want you guys to see that they were there. And we're essentially finishing with the result. I guess I can copy and paste. Copy, paste. This is equals. Undo. That's fine. There we go. All right. Yeah, I think we're okay. 8 e to the 8x. Okay, I think we got those two. Yeah, I think we got all of these. All right. Let's see what else we got. Just a quick check. Okay. So find the second derivative of y with respect to x for y equal to this. All right. So basically, I think we talked about higher order derivatives toward the end of chapter 1. All we're going to do is take the derivative like normal, we get a result, and we're going to take the derivative again. Right? Okay. So then first let's find dy by dx. So e is its own derivative. So there's going to be e to the negative 5x squared, but then we need to say times the derivative of the power. It's going to be what? Negative 10x. Okay. So then from there, then with the second derivative, it looks like we have to apply the product rule. First times the derivative of the second, plus the second times the derivative of the first. Okay. So the second derivative of y with respect to x, the first, which is this, the times the derivative of the second is going to be this, plus the second, which is this, times the derivative of the first, which is basically, I'm just going to copy and paste because it's going to be a repeat, right? Yeah, it's going to be a repeat of this. Copy, paste. Okay. Let's see what simplification we can do. It looks like both terms have this e to the negative 5x squared, also with a negative 10 that we can factor out. So it looks like we can factor out a negative 10 e to the negative 5x squared, okay, from both terms. In the first term, it looks like we're left with a 1. In the second term, first times the greater second, yeah. So that doesn't have the x. So we took out one of the 10s. We took out the e. Looks like we're left with double negative becomes positive. Wait a minute, I lost track. Okay, we got our 1. Here, let me see. That's gone. The 10 is gone. So it looks like we have a negative 10x squared that remains there. Okay. And I think that's about the best that we can do. Paste. Oops. Copy. Okay, I think we got it. Let's just compare it to the prepared notes. Okay, so that's the first derivative. Okay, let me see. Yeah, so all they did was distribute the negative, and it basically flips everything. So that's going to become 10x squared minus 1, right? They just distributed a negative into the parentheses. Otherwise, we got the same thing. Okay, 2 different ways of expressing the same thing. Let me try to wrap this up. I think we can do this example. Franco's Fishing Emporium invested $50,000 in an account that earns 1.25% annual interest compounded continuously. The value of the account after 2 years is given by this. Find the amount in the account after 5 years and find the rate of change after 5 years and interpret their meaning. Well, A of 5, we just plug that in, you get an answer. A prime of 5, we need to take that derivative. Okay, let's find A prime. So then A prime is going to be 50,000. The derivative of E is itself times the derivative of the power. That derivative is just going to be this number, 0.125, 0.0125. So then if we want A prime of 5, we plug in 5 for T into this guy. So then for A of 5, and let me see, that's going to be the amount in the account after 5 years with these conditions, right? 50,123 times E, 0.0125 times 5, okay? 5 years, they only earned $3,000. 30. It's always disheartening. I see that. We're gonna need a bigger principal for it to be like anything substantial. Let me see. Okay. So here we get approximately 53,2224.72. And then the rate of change of the account at 5 years. $50,123 times E to the power of 0.0125 times 5. Okay, and then we're going to say times. So we could have just said that answer times 0.0125, right? We didn't have to retype all of that, but that's okay. So what we're saying that the account is growing by $66 a year? No. That's the rate of change. At that moment in time, that's the rate of change of the account. Why does that something seem off there? Anyway, I mean, I feel like the number's good. 6653. Okay. I'm just gonna highlight it like this. Let me see. Okay. Oh, 665. What are we missing? Okay, I think we made a mistake somewhere. That sounds like that number seems kind of weird. 665 makes more sense. Let me look at these numbers. I put, okay, in the calculator, I put 5,000. That's supposed to be 50,000. So that's where the error is coming in. I was like, because, okay, so it's supposed to be the rate of change, the amount of growth is growing, but 66 was too small. I was like, that seems weird. So it really should have been 665, right? And I typed it in the calculator wrong. So I'm going to go ahead and insert, change it to 50,000. So now we get our 665, 665, 31. And then that makes more sense that the account is growing by $665 per year, right? Yeah, initially I typed it in the calculator wrong. That's why that number was like, why does it seem weird? That makes more sense, right? Because, almost $700 a year. But that's the rate of change in 5 years. It's going to change each year, but it's an approximation. So, yeah. Okay, it feels better. Okay. So after exactly 5 years, the value of Franklin's Fishing Emporium account is going to be $53,224.72, and at that instant, the value is growing at a rate of $65.31 per year. Right? Okay, that makes more sense. Okay. So I think that got us to the end of this section, right? So here we introduced again, looking at or exploring the derivative of the exponential. Remember, the exponential e is its own derivative. And then if you ever have e to the power of a function, when you take that derivative, it's still going to be itself times the derivative of that power. Okay. If there aren't any burning questions, we're going to go ahead and end the session here. From one beautiful mind to another. Enjoy your evening, gentlemen. We'll meet back on Wednesday, same time, same place. Take care. Peace. Any questions, gentlemen? Going once, going twice? All right, gentlemen. I'll see you next time.